one last thing I want to talk about before we stop talking about physical layer. That is the following. Link budgets. So what the physical layer does for you is it gets you a signal. It gets you a particular signal strength. So all of the issues that we've been talking about, basically, where they impair you is in terms of, or where they help or hurt you is in terms of the signal strength at the receiver. So all the other layers basically have to overcome any inadequacies in the physical layer. In other words, if the signal drops out, the upper layers have to figure out a way to get the data to you by other means. So at the end, what you will generally find is that there's a certain minimum amount of power that you expect to have at the receiver in order to allow your system to function. A link budget helps you calculate how much power you have to start out with in order to have the required amount of power at the end under all possible scenarios. So the reason it's called a link budget, it kind of looks like a budget. So you start out, let's say you want to go on vacation, and in order to go on vacation, you need $1,000. So at the end, you need $1,000. Starting out at the beginning of the year with your regular salary, which is $10,000 or something. So you'll then deduct the expenses you need for food, deduct the expenses you need for rent, and so on and so on and so on. And hopefully at the end of that, you will find that you have $1,000 left. So we're going to do much the same thing here, except in terms of signal strength. So we'll say we start out with, in terms of signal strength, subtract this for this kind of loss, subtract that for path loss, subtract this for fading loss, and so on. And at the end, we come up with the power we hopefully need to communicate. So a link budget counts for losses between transmitter and receiver. So we would like a budget to be something that we would subtract from, or we'd add to or subtract from. Unfortunately, most of the losses in wireless communication that we've seen so far are multiplicative. In other words, when we amplify, we multiply by a certain value. The fading loss, that's a multiplicative factor in front of the sinusoid that we're interested in. So gains and losses are multiplicative, not additive. So can anyone think of a way that we can get from these multiplicative losses to something that's add and subtract? Take the log of it, there we go. So we're going to take a short digression into what's called decibels. Who does not know what a decibel is? Everybody knows what a decibel is. Yeah. Don't be shy. Okay. Just so everyone is absolutely on the same page. A decibel, if I have a factor, let's say k, and I want to express that in terms of decibels, what do I do? 10 log what of k?
Log base 10.
Log base 10. Okay. So let's call that capital K sub dB. To get back from capital K sub dB to regular, what do I do? I want to get back to regular, from dB to regular.
10 to the
10 to the K over 10. 10 to the K dB. 10. Okay, some fun things to remember about decibels. k is 2, n log 10, 2 is roughly equal to what? Anybody know? It's roughly equal to 3. It's really super close to 3. So usually when we say 3 dB, we mean a factor of 2. So if I give you, let's say 30 dB, what's that equal to in regular? It's 1,000. So generally, if I give you a round number like, this isn't a real number, but like some digit, let's call it D0 dB. So this is just where D represents the first digit. This isn't multiplication, it's just the first digit is D and the second is 0. That is generally equal to 10 to the power of D. So 10 dB equals 10, 20 dB equals 100, 30 dB, 1,000, and this is the whole point of using dB. It's a nice shorthand. So you look at the first, the leading digits, and that gives you the power of 10, and then the next digit sort of gives you how far it is up to the next power of 10. Yes.
You said generally.
Generally?
Yeah, like generally it's equal to 10 to the D, and in case you can think of it's not that.
If I said generally, then I was just
Just means that you would-
using a figure of speech. That's right. So you wouldn't hold this against me in a court of law. No, that's. I mean, it's just a mathematical relationship, so that's always true. Sorry about the imprecision. Just one other thing to notice. So you can. So if I have A times B. And A in decibels is A sub dB, and B in decibels is B sub dB. Then if I were to convert A times B to decibels, what would I do?
A plus B.
A dB
decibel
plus B dB. Okay, so given all of that information, 23 dB is approximately equal to what? 20 plus 3, so what's each of those in non-decibels?
102.
You're on the right track. You're on the right track.
100 and 2.
So 20 is 100 and 3 is what? 3 is 2. So if I added 20 plus 3 to get 23, then what do I do in the other domain?
Multiply.
It's 200, roughly 200. So let's try 27 dB.
That's just 30 minutes speed.
Which is
1,000 times 2.
so when I subtract. Okay, it's kind of a trick.
Oh, it's division.
I'm subtracting its division. So it's 1,000 divided by 2, which is roughly 500.